everyone. Welcome back to the lectures in Introduction to Multi-Agent Systems. In the previous lecture, we saw that we had a set of n agents, and we divided these agents into two groups. The first set of agents served as the followers, and the others were the leaders of the network. Now, the role of the leaders was to ensure that the states of the followers, or rather, the role of the leaders was to be able to steer the states of the followers from any initial condition to any desired final condition. This is also known as leader-follower controllability in multi-agent systems. So in today's lecture, we'll try to understand when exactly can a system be leader-follower controllable. And to be a bit more specific, we'll try to understand this for the case of undirected networks. So let's get started.
Consider a group of interconnected agents that satisfy the following. One of them acts as a leader and receives external inputs. Because there's just one leader, let's say, receives an external input, U. The rest of the agents have single integrator kinematics and are governed by the Laplacian flows. This is the important part. So if you remember, we had partitioned the network into two set of states. Let's say if X dot is the overall n cross 1 state vector where group of n interconnected agents, then X has a dimension of n cross 1. Suppose we now divide the states into two parts. XF, which is the followers dynamics, and X leader. Then it's modeled in this manner. Minus of LFF, LFL, and these two entries continue to be 0. XF, XL, plus the leader is the only one who's exposed to some input, external input. Again, just a quick reminder, LFL here is a column vector. LFF is an n-1 cross n-1 square matrix. So if you observe here that the state XL associated with the leader affects the followers through this column vector LFL. Meaning, so now let's rewrite the dynamics. We have XF dot, which is the followers dynamics, is minus of LFF times XF minus of L. FL times XL. And the leader's dynamics, XL dot, is simply driven by UN. Okay. So our primary focus is on the dynamics of the followers. And we are now interested to see if XL, which now serves as an external input to the system of followers, can this external input actually drive the followers in the network? Meaning, it boils down to a standard controllability test. So let us now get started with the controllability of the system. So if you now try to mirror it in terms of the standard LTI systems that we know, we would write the dynamics in this manner. So we know X dot is AX plus PU in the standard form. Then the controllability matrix is given by B, AB up to A raised to the power n minus 1 B. Using this, we can say the interconnected system of followers is controllable by the leader if and only if the corresponding controllability matrix is full rank. So all that we have to do now is write down what will be the controllability matrix. So notice that this here acts as the A matrix and this here is a B matrix. So the controllability matrix for the system is given by C is equal to the equivalent of P is minus LFL. So we write minus LFL times AB. So equivalent of A is minus LFF. So this product simply becomes LFF times LFL. And the next term will have a minus sign and becomes LFF squared LFL. And this goes up to the nth term. The nth term is now equal to minus 1 raised to the power n LFF raised to the power n minus 1 times LFL. So this is our controllability matrix. The entire system is controllable by the leader only if this matrix C has full rank. So now we have to explore the conditions, especially the topological conditions under which C will now have full rank. So to begin with, let us apply the results that we already know. So before we get into computing the rank, we'll do a quick recap of some of the things that we have discussed before. The first thing is, since G is undirected, the underlying graph that's given to us, we are assuming that it is undirected. Then Laplacian is a symmetric matrix. Consequently, so also remember that LFL and say this is LF and L. So remember that L is a symmetric matrix. Then when we partition L in this way, LFF will also turn out to be a symmetric matrix. This is a very useful information as it now allows us to use a lot of nice properties that we already know about symmetric matrices. For example, we know that, let's write this as the first point, then the second point is, we know that the eigenvectors of a symmetric matrix are orthogonal to each other. In fact, we can even make them orthonormal, such that the norm of each eigenvector is equal to 1. In this case, since the eigenvector is always orthogonal, let us denote U as the set of all the eigenvectors, the matrix composed of all of the eigenvectors. Let's write it. Composed of the eigenvectors as its columns. Okay, now let us say that the symmetric matrix that we are looking at, instead of keeping it a generic symmetric matrix, let us say of the symmetric matrix LFF, and U is the matrix composed of the eigenvectors as its columns. So let's modify this slightly. Eigenvectors of LFF, meaning what is now the dimension of U? U's dimension is n minus 1 cross n minus 1. Because LFF is an n minus 1 cross n minus 1 matrix. Applying the Chorton decomposition, we can now write, hence, we can express LFF as LFF is equal to U times J times U transpose, where J is a diagonal matrix with the eigenvalues of LFF as its diagonal entries. Further, let me again quickly remind you of one more thing, that if it is a symmetric matrix, then all of its eigenvalues, so if LFF is a real symmetric matrix, which in our case it is, then all of its eigenvalues are also real, meaning all these eigenvalues of F are in fact real valued. And this is how we can decompose F. Now, in order to find the conditions such that the controllability matrix given here does not lose rank, let us first apply these properties of the symmetric matrix on the controllability matrix C. To do so, let me copy this first. So now we are trying to explore the conditions for controllability. And for us, this is the form that the controllability matrix takes. So we know that LFF, let us substitute the value of LFF that we now know. So this is minus LFL. LFF is U, J, U transpose times LFL. And the next term similarly becomes uj u transpose whole squared times, so there's a minus here, and LFL. The last entry here is minus 1 raised to the power n uj u transpose to the power n minus 1 times LFL. Now, what does this power look like? uj u transpose raised to the power k. This simply means we have uju times uju, and this product is actually repeated, uju transpose. This product is repeated k times. We know that u transpose u, because u is an orthogonal matrix, u transpose u is equal to identity, meaning every time we have u transpose u, we can replace it with identity. We can do it here, we can do it here, we can do it here. So effectively, what we are left behind is just the Jordan matrices, meaning this simply is equal to u j raised to the power k times u transpose. So let us substitute this result into our controllability expression. It gives us C is now equal to minus LFL times, the first term remains as it is, uj u transpose times LFL. The second term now becomes u j squared u transpose LFL. And the last term is similarly given by minus 1 raised to the power n times u j raised to the power n minus 1 u transpose times LFL. This is our controllability matrix. Let us see if we can now simplify this expression somehow. In order to do that, let us rewrite it. So the first term here, we can write this as minus identity times LFL. And we know that u times u transpose is equal to identity. Hence, the first term can be rewritten as u transpose times LFL. And the second term is equal to u j u transpose times LFL. Similarly, the last term here is equal to minus 1 raised to the power n u j raised to the power n minus 1 u transpose LFL. What we can do here is we can take u outside, and we are left with minus u transpose LFL times j times u transpose LFL up to minus 1 raised to the power n j times n minus 1 u transpose LFL. This simple rearrangement actually makes the analysis of the controllability matrix much, much easier. Why does it happen? Let's see. We know that U consists of the orthogonal eigenvectors or orthonormal eigenvectors of LFF, which implies that U is non-singular. Because all of its column vectors are now linearly independent. So obviously, U now becomes a non-singular matrix. So C, the matrix C here, loses rank only if now the second term here, which is this big expression, if this matrix now loses rank. So what happens with this matrix? What can we say about this? Let's see. If you observe closely, now let me write it separately here as some new term. So I'll write it as C prime, and I'll explain shortly why are we again writing it as C prime, because C stands for a controllability matrix. So it's the second term like a controllability matrix. Let's see. So it is minus U transpose LFL, J times U transpose LFL. This goes up to minus 1 raised to the power n, J raised to the power n minus 1, U transpose LFL. This matrix. Again, if you observe closely, this term can be treated as the B matrix of a certain system, and this J here can be treated as the A matrix. Then again, we have the same formulation. B, A times B up to. So just remember here that A would be minus of J, and B is minus of this entire thing. So the last term, that's why here becomes minus 1 raised to the power n, J raised to the power n minus 1, U transpose LFL. So meaning A to the power n minus 1 times B, which again takes the form of a controllability matrix of some reduced system. Either way, while we are not particularly interested in that system, but we are certainly interested in figuring out when this matrix loses rank, which will be focus of the next part of the lecture. Again, why is it important for this matrix to not lose rank? Because if this matrix loses rank, then what we already know is our controllability matrix is nothing but U times this matrix. If C prime loses rank, then C also loses rank. Hence, if C loses rank, then we know that the system is not controllable, meaning the leader will not be able to drive all of the followers to any desired position. So let us focus on C prime. The matrix C prime consists of, or let's write it this way, the ith column of C prime is given as minus 1 raised to the power I, J raised to the power I minus 1 times U transpose LFL. So this consists of effectively two terms. The matrix J, which is nothing but a diagonal matrix, and the matrix U transpose LFL. So what does the power of a diagonal matrix look like? Let's write it. J raised to the power I minus 1 simply looks like this. We know that J is a diagonal matrix, and along its diagonal entries are the eigenvalues of the matrix LFF. So we can write it as lambda 1, which is the first eigenvalue, raised to the power I minus 1. Then lambda 2 raised to the power I minus 1. The last eigenvalue is lambda n minus 1, again raised to the power I minus 1. So what happens when we multiply a diagonal matrix with a vector? Remember that LFL is nothing but a row vector of dimension n minus 1 cross 1, and U transpose is an n minus 1 cross n minus 1 matrix. Hence, this entire thing is nothing but an n minus 1 cross 1 column vector. So this is j raised to the power I minus 1. Let us now multiply the matrix j raised to the power I minus 1 with some vector u transpose LFL. So let me simply randomly write it as some vector rho 1, rho 2 up to rho n minus 1. Suppose u transpose LFL, the column vector is now equal to rho 1, rho 2 up to rho n minus 1 transpose, which is what we have substituted here. Then what does this do? Let me instead write it here. The outcome of this is, so please pause the video here and try it by yourself first. It is a very simple calculation. If you try it, what you would get is, effectively, when we multiply a diagonal matrix with a vector, we scale along all of its dimensions. So this is a very important term. This implies j raised to the power I minus 1 u transpose f u transpose LFL is simply equal to lambda 1 raised to the power I minus 1 times rho 1, lambda 2 raised to the power I minus 1 rho 2, and lambda n minus 1 raised to the power I minus 1 times rho n minus 1. All that happened was each of these entries of U transpose LFL simply got scaled by the diagonal entries. So now, if I am to write up the entire controllability matrix, then what will it look like? So the first term simply is U transpose LFL, and U transpose LFL, we have written its entries as rho 1 to rho n minus 1. The second column is lambda 1 rho 1, lambda 2 rho 2 up to lambda n minus 1 rho n minus 1. Notice that we have missed something here. What have we missed? We have missed a negative sign. So this entire column has a negative sign to it. Similarly, this keeps on repeating. And the last column is minus 1 raised to the power n times lambda 1 n minus 1 rho 1, lambda 2 n minus 1 rho 2 up to lambda n minus 1 raised to the power n minus 1 times rho n minus 1. Now, with this construction, we can very clearly now say, so, okay, again, this should be multiplied with U transpose because we have written C and not C transpose. Okay, not U transpose, just U. Okay, so this is our controllability matrix, and we know that U has full rank. So now we can very clearly state the conditions under which C has full rank. The first condition, suppose one of the row i's is equal to 0. One of the row i's is equal to 0. Then what happens to the controllability matrix? Let's copy this and duplicate it. We are saying one of the rows is equal to 0 without loss of any generality. Let us say that row 2 is now equal to 0. Then how does this matrix change? We see that the entirety of the second row of the controllability matrix will now turn to a row containing all 0 entries, meaning obviously C has lost rank. And if multiple entries of the column vector U transpose LFL are equal to 0, then those many rows turn out to be rows containing all 0 entries, meaning in all such cases, C loses rank. So let's write a conclusion. This implies the very important condition: C loses rank if one or more entries of U transpose LFL is 0. What is U transpose LFL? It simply means that the matrix, the column or the column vector LFL that we have must not be orthogonal to the eigenvectors of the matrix LFF. This condition is now equivalent to saying, what is U transpose? U transpose, just to remind you, U transpose or U simply consists of the eigenvectors V1, V2 up to Vn. U transpose is just, let me write it. So you're looking at U transpose LFL. So we multiply LFL to it. So now we are saying some of its entries are equal to 0. It would mean we are now multiplying. So since we have taken a transpose, we will have V1 transpose, V2 transpose, up to, this is n minus 1. Please remember that U is n minus 1 cross n minus 1 matrix. So this is n minus 1 transpose. And this gets multiplied with LFL. So this again can be expressed as summation of V1 transpose its ith entry multiplied with LFL's ith entry summed over I to n, and this gets repeated. Vn minus 1 transpose I, LFL I. If any of the entry here now takes a negative, becomes equal to 0, it means that V transpose LFL is equal to 0. Let's write it. If any entry, if let's say the kth entry is equal to 0, let's write it. If, or the, because we have used k to express the powers, let's write if the pth entry of U transpose LFL is 0, then we say that Vp, the pth eigenvector, its transpose times LFL is equal to 0, meaning Vp is orthogonal to LFL. Hence, if we can ensure that none of the eigenvectors actually orthogonal to LFL, then we move closer towards the controllability of C. Or sorry, we move closer towards C having a full rank. But this is not enough. Let's go back to this expression. What we have ensured is, suppose we ensure that none of the eigenvectors are orthogonal to LFL, then we know that none of the entries here, none of the rows of C prime become equal to 0. Let us take into account another condition in which the matrix C can actually lose rank. What is it? To understand that, let me again copy this. Okay. So this is a controllability matrix. And as before, we want to make sure that it doesn't lose rank. Let us see one more condition under which C can lose rank, or C prime. So what happens is first C prime loses rank, owing to which C loses rank. C can lose rank, or let's start with the condition. Without loss of any generality, let us assume that λ1 equals λ2. Then what happens to a matrix C? This is the second condition under which it can lose rank. So the first condition was about orthogonality, where we said that one of the row i's is equal to 0, which was like saying VP, some eigenvector VP is orthogonal, then it loses rank. Now we're exploring the second condition, for which we say, suppose λ1 equals λ2, then let me bring the controllability matrix here. And we write this as second condition for C prime equivalently C to lose rank. So here, first we say that let any two eigenvalues become equal, and without loss of any generality, we say that suppose λ1 becomes equal to λ2. And suppose this is equal to some value equals lambda bar. Now, how does the C matrix change now? Let us write it. What do we observe here? We observe that the two rows, the first row becomes exactly the same as the second row, meaning the rows now do not remain linearly independent, meaning the matrix C prime now loses rank. This implies two rows of C prime become linearly dependent. Implies C prime loses rank. Implies C loses rank. Notice that it doesn't matter which two eigenvalues become equal. We could have just taken the first and the last eigenvalues to be the same, and the same thing would have happened. So whenever any two eigenvalues become the same, then the controllability matrix loses rank. Let's summarize it. This implies whenever any or whenever two or more eigenvalues of LFF become equal, C loses rank. So now we have found two conditions, and if we can ensure that these conditions do not happen, then the C matrix will always have a full rank. So let us now sum up these results. And highlight it as the main result of today's discussion. We say that given the framework that we have, the leader-follower framework that we have, such that the leader is driven by an external input. So very quickly, so a group of agents driven by the Laplacian flow and a leader, such that its dynamics x follower dot is equal to minus of LFF xf minus of LFL times the state of the leader, which is XL. Under this framework, the leader whose state is given by XL can control the followers whose states are given by XF under two conditions. We can write if and only if. The first condition is, let's write it as C1. The first condition states that all the eigenvalues of the matrix LFF must be distinct. The second condition, C2, now says that the corresponding eigenvectors must not be orthogonal to the column vector LFL. So these are the two conditions under which we can ensure that the leader can always drive the system of followers, the interconnected system of followers, towards any desired state. Let us try to understand these results a bit better by looking at an example. Consider the undirected network shown in this figure. As you see here, the node in green is the leader node, and the rest of the nodes in blue are the followers. And we also see that the leader is subject to an external input U. So we now try to apply the leader-follower dynamics that we know. For that, let's start by writing up the Laplacian matrix. And 2 is connected to 4 and 3. And node 3 is connected only to 2. And node number 4, in the Laplacian framework, it's connected to both 1 and 2. Remember that we will now try to split up this matrix in two different forms. the set of leaders and the set of followers. Okay. So the leader nodes VL, it simply has just one node 4, and the set of followers consists of 1, 2, and 3. Such that this entire matrix, or submatrix rather, is our LFF. And this matrix here is our LFL. And we know that the other two matrices simply go to 0. Hence, we can say the leader-follower dynamics is given by, let us bring this entire thing here, and what is not needed, let's remove it. And now, to apply the leader-follower framework, the leader is not influenced by any of the followers. This is XF, which is a 3 cross 1 column vector, and we have XL, which is a scalar. This is 0 and U4. Or we can say simply U. And on the LHS, we have X dot, which is XF dot and XL dot. It's given by this. So the followers dynamics can be extracted out as X dot is equal to, so what we have missed out is the negative sign here. So in the Laplacian flow, we have negative of the Laplacian. So hence this gives us LFF. This is LFF and this is LFL times XF minus LFL times XL. So what are the conditions we studied which ensure the controllability of all of the followers by the leader state? The conditions rely on the properties of the matrix LFF. And what are the properties? The first property says that all of the eigenvalues of LFF must be, first of all, distinct. They should not be repeated. The second is all of the eigenvectors, the orthonormal eigenvectors of LFF, must not be orthogonal to this row vector here, to this column vector, given by LFL. So now let us check if these two conditions hold or not. To begin with, again, we know that, or let's write it, since LFF is a symmetric matrix, we can express it as LFF equals U, the Jordan matrix, times U transpose, where U is the set of all orthonormal eigenvectors. If we do the computation, we see that here the matrix U turns out to be, or let's start first with the eigenvalues, which is a first test. The eigenvalues of LFF, which appear as diagonal entries of the Jordan matrix, are minus 2.6, 2.61, or just 2.6, say 1 and 0.38. So what do we see? We see here that all of the eigenvalues of LFF are actually distinct. So how do we, just to remind you, we compute the eigenvector of any matrix simply by doing this. And then we can arrive at the eigenvalues by solving for lambda here. So we see that we have passed the first test. All of the eigenvalues of LFF are actually distinct. Now we move to the second test, which is about the orthogonality of the eigenvectors of LFF with respect to LFL. So let us check that condition. But for that, we must know what are the eigenvalue vectors to begin with. So let us write up the eigenvector matrix. If you do the computation, you see that it turns out to be so let us multiply this with the row vector LFL. So these are the set of eigenvectors. And now we multiply them with LFL. What is LFL equal to? Let's go back to our expression. LFL is equal to this column vector, -1, -1, 0. And what does this add up to? This is simply equal to -1, 0.85 and -0.525. What do we see? We see that none of the entries of, oh, my bad. We now need to check the condition of orthogonality. So in order to do that, we do the computation U transpose LFL. So let's write the matrix. And LFL is equal to, as you can see here, -1, -1, 0. Let's write it here, -1, -1, 0. And this becomes equal to, let's make some space here, 0.85, -1, and 0.525. So what do we see? This implies that none of the entries of U transpose LFL is 0. Implies none of the eigenvectors of LFF is orthogonal to LFL. Hence, we had two tests. In the first test, we saw that all eigenvalues of LFF are distinct. In the second condition, we saw that its eigenvectors are also not orthogonal to LFL. Hence, according to our result, so this must imply that C must be full rank. So let us compute, is it really full rank? So now we can simply construct the controllability matrix using the expression minus LFL, then LFF times LFL, and minus LFF squared times LFL. When we do that, if we compute the rank of C, it turns out to be 3, meaning that C has full rank. Meaning the test that we had actually gives us the correct result. We see that C does in fact have full rank. So there are many ways to compute the rank of a matrix. So we can, use the standard ways to compute the rank here. And interestingly, what this says is, this further implies that the system is leader-follower controllable. With this, we'll end today's lecture. In the next lecture, we'll look at some very specific graphs and try to see if they are leader-follower controllable or not. In that way, we will also try to figure out if topology can play a role in this controllability. Thank you.